Alright gang, here we go. This is for Physics Unit 9, Part 6.1. We're going to talk about series and parallel circuits. Alright, so when we're looking at something like this, these three circuit diagrams, what we've got is we've got a light bulb all hooked up to our battery, right? And our electrons flow this way. Our conventional current flows around the opposite way, okay? And what they're asking is, and then we've got them in series, and then we've got them in parallel, okay? And so when we're looking at this guy, we got to think about what will our brightness look like. So if we're comparing the brightness of bulbs B and C compared to each other, all right, these two guys should have the same brightness, remember, because the brightness of a bulb is dependent upon the energy that's passing through it, right? And that energy is dependent upon the current and the charge, right? And really current is dependent upon the charge. So the light bulbs will be the exact same brightness because they have the same current passing through them. All right, so those two should be equal to each other. Now the current that's passing through these would be equal to the current that's passing through A. So these guys, you know, if we were comparing the current to A to the current of B and C, or the current of B to C, they would be the same. But since A only has one, and we have to have the conservation of energy, A would be much brighter than B and C would be. Okay. Now, then we look at D and E. Well, these would be the same brightness because they're going to have the same potential energy drop. They're going to have the same voltage drop across the two of them. All right, and so therefore, as they go across, you know, as our electrons travel across here, they're going to have the same potential energy drop. All right, and in fact, they'll have the exact same potential energy drop as A does. So their brightness should be equal to A. Now, but you think about it, if their brightness was equal to A, but you're lighting up two of them, that means the current has to increase, right? So the current would have to be the same in the first two, but your current would have to be much bigger in this last one. All right, now, and part of what we're going to explore today, well, how much bigger? Your instinct might just say it's twice as big, but that's not necessarily true. All right, now before we move on, what I want to do is set up a little I want a screen. We're going to think about, you know, what we've kind of established. Remember, we talked about how we can use the idea of water flowing through pipes in order to think about current. Now, what I want you to think about is thinking about a water slide. All right, so say you've got a water slide, and this is where you start. This is where you get on your little boogie board, and you're going to drive down your water slide. Okay, as you go down your water slide, you come down here, you hit a hill, and you might hit like a flat spot, and then you hit another hill, and you come down, and you go to the pool. Now the water behind the scenes, right? So this is the person. This is where they're going to ride. They're going to go that way. All right, and then as they, you know, they go down here, and then once they hit the bottom of this thing, the water doesn't just chill down here. They need water back up the top, because if you've ridden on a water slide, you know there's constantly water going down there. Otherwise, it wouldn't be a water slide. It would just be a slide. So what needs to happen is this water needs to get pumped over here. So you got to send it through some sort of pump, all right, in order to send it. Really? Pump in order to send it and fight against gravity to send it back up the hill so it can go back down the hill again. And so we would call this conservation of energy because up here the water has a lot of potential energy, falls down, loses its potential energy to kinetic energy, gets to the bottom and stops, and then it flows over here and then it gets pumped back up, right? And it exchanges this mechanical energy for potential energy again. All right, same thing happens with the circuit, only instead of thinking about, you know, we're going to think about, instead of gravitational potential energy, we need to think about electrical potential energy. So when our electrons are up here, we have a high electrical potential energy, and then as we go down, we're going to lose electrical potential energy. So each of these steep places here are places where we're actually losing electrical potential energy. Right here, it's flat. We're not losing any potential energy right here. We're just traveling. So here, the places where we lose electrical potential energy, those are like our bulbs or our resistors. All right, so here's a bulb, here's a bulb. All right, and then this flat part here, this would be a flat spot. So this is where we're not losing anything. So this would just be the wire of our circuit. All right, and so the electrons would come down here, and then they come back and they flow through here. But then we need something to pump them back full of electrical potential energy. So this would be equivalent to the battery, all right, or whatever our EMF source is. All right, so and that's really what we come down to. So if we kind of keep this into our mind as we think about our electrical, or think about our circuits, it makes some of these ideas that might seem foreign a little bit easier to grasp. Okay, so resistors in series of resistors are when you have a circuit that provide a single path for the electrons. Okay, so single path for the current. There's only one place the electrons can go. They can go out and they can go around and then they can come back again. So in order for this current, in order for an electron to go from here and across, it needs to pass through both of these resistors. That's its only choice. So we call this a series circuit. Okay, now in a series, no, not you, Siri. Not you, Siri. I said series, and she thought I was talking to her. But anyway, so that we call this a series. All right. So this is a resistor in series. All right. So we've got now every time I say it, I think she's going to start talking to me. All right. So we've got now because then think back here to this. Oh no, it deleted my thing. So we think about our water slide. Okay, our potential difference, you know, we could have a water slide where we have a big drop for the first slide, right, and then just a little drop for the next one. So if that's our slide, this would be our pump again, all right? So these potential differences don't have to be equal to each other, but they both have to equal the total height of the slide, right? Same thing with our electricity. In a series circuit, all right, then the pump of our battery has to, the total distance traveled, or the potential difference dropped by our electrons as they pass through the bulbs, has to be equal to the total pump energy that was put into it. So and we call this the conservation of energy. Now, and so this is our first big idea when we talk about series circuits, is that the potential energy, the potential difference of each of them have to be add up to be the total potential difference. Now we know because of Ohm's law, and this is a really important one, delta V equals the current times the resistance. This is going to be really important in the next video when we talk about complex circuits. When we look at this guy here, our potential difference is equal to I times R, all right? And so what we can say, well, if our potential difference is equal to I times R, then our I times our R is, we can just plug that guy in here. So the delta V of our battery, potential difference of the battery, is just equal to I times R1 and I times R2. Now you might be thinking, why isn't it I1? Well, that's because the current is always the same for a series circuit. Remember that our current is really just the charge, right? Our current is equal to the charge per second. All right, so in any given part of our water slide, the same amount of water has to be traveling through it at the same time. If there was more water traveling through it at one time, then you've either created new water from nothing or made water disappear. And either way, you're God, and you don't need to take high school physics. All right, so you've got current, all right, is equal to charge per second. Okay, and so these currents are going to be the same. This is essentially what it comes down to. So IR1 plus IR2, and that's your Ohm's law. So your potential difference of your battery, we can pull the I's out and we get this one, all right? And then we also know that from Ohm's law that the potential difference of the battery is equal to the I times the equivalent resistance, or the resistance of everything added up. And so then really we can pull over our delta VI and we can set this equal to each other. And so we get this guy here, all right? So really there's three important ideas, all right, with series circuits that you need to be aware of. We have this idea here, that our potential difference of the battery is equal to the sum of all the potential differences of the circuit, and the equivalent resistance is just equal to all the resistances added up. The last one has to do with current. The current of the battery, or the total current, has to be equal to each of the currents over each of the different things that are involved, each of the different elements. All right, and so I1 would be equal to I2, which is equal to I3, which is equal to I4, etc., etc., etc. All right. So this is our equivalent resistance formula here. All right, Req equals R1 plus R2 plus R3. All right, so the equivalent resistance is equal to the sum of the individual resistances of the series. All right, so if you're solving a problem with resistors in a series, these are the general steps. Always, always, always find the equivalent resistance first. And this really applies to any circuit. If you always find that, you've always got at least one foot in the door. Then once you have the equivalent resistance, you can use this to find the total potential difference, or the current. Once you have that, you can use those and the individual resistances in order to find the potential difference of each individual spot in your circuit. So let's give it a shot. It says a 6-volt battery is connected to each of the following bulb combinations. Find the current in each circuit and the potential difference across each bulb. All right, so it says a 1 bulb with a resistance of 7.5 ohms. All right, so we've got some sort of battery hooked up, and then we've got our current, our resistor, okay, and it says a 6-volt battery, so we'll put 6 volts, and then that'd be 7.50 ohms. All right, and they want us to find the the current in each circuit and the potential difference. Well, current, remember, and we're just going to write this up here because we're going to refer back to this over and over and over again. Delta V equals I times R. So that means our I value is going to be equal to our delta V over our R. All right, so delta V is our 6 volts. All right, 6 volts, and our resistance is 7.5. 0 ohms. So that means, where'd my calculator go? So we take 6 divided by 7.5. Oh my goodness. 6 divided by 7.5. And we get 0.8. All right, how many sig figs? 3 sig figs. That's awesome. All right, 0.800 amps. All right. Now we do the same thing. Now we have 2 bulbs in series, each with a resistance of 7.5. Well, this is easy, right? Same idea here. Our current is equal to delta V over R. All right. Now the delta V value, well, that's just how the potential difference. So that's just still 6 volts. And the resistance, though, the resistance is equal to, well, the resistance is the total resistance, and there's 2 of them in series, and we know that when we have them in series, they're just added up. So that'd just be 2 times 7.5, which are 15, right? So that's the total resistance of our circuit. So we take 6 divided by 15, and we get 0.400 amps. All right, and then the last one, we have 4 bulbs in series, so our current is equal to 6 volts. Again, I'm not going to rewrite that part. 6 volts over 4 of these guys. All right, 4 times 7.5. So we have 6 divided by 4 times 7.5. We get 0.200 amps. All right, so that's the current for each of them. Then they ask us to find the potential difference across each bulb. Well, the potential difference across this first bulb will be easy, right? Because there's only one resistor, and we know, remember, for series circuits, the potential difference of the battery is equal to the potential difference of each one of these all added up, right? Etc. All right. And so when we have just one bulb, that means their potential difference of the battery has to equal the potential difference across the one resistor. All right, so that one's easy. So the potential difference across this one, our V1, is just equal to 6 volts, 6.00 volts. All right, and then for the second one here, now we have 2 of them. So but they happen to have the same resistance, so that makes life easier. So the potential difference of both of these guys would just have to be half of that, so it would just be 3 volts. All right, and then the last one here would be the same idea, but there's 4 of them, so the potential difference across each resistor, well, maybe we should call this resistors, across each resistor here would be 1.5, right? 6 divided by 4, all right? And sure enough, these are the same answers that I got earlier. Thank goodness. All right. Now we have resistors in parallel. Now parallel resistors act a little differently. Remember, we established before that a parallel resistor will have the brightness of the bulbs be exactly the same as they were before. Now, so what this essentially means, what you should think about this is remember, we've got our water slide, and as it comes down, whatever, and we can have the hills however we want. Imagine that before you started, you had 2 paths, right? So you had 2 paths that you could go down. So imagine that there was a second path that only had, had one giant hill that went down instead of 2 separate ones, right? Or 3 or 4 or whatever. And so you have essentially have a second path that you can take. All right. Now, if you have that second path, that means that potential difference has to be the same because they need to go down the same amount. So the potential difference has to be the same for both of them. All right. So this is an important idea. The potential difference has to be the same because they need to lose the same amount of energy. Well, that means that if the potential difference has to be the same, that means the current has to go up. All right, so essentially what this means is that the current has to be each of these current values added together have to equal the total current, and this would be the conservation of charge, because for each of these potential difference drops we're going to be using a certain amount of charge, and since each of those potential difference drops have to be the same, that means we're going to be using a certain amount of charge depending on the resistance in that specific branch. All right, so what does that mean exactly? Well, this is an important idea, that the current of the battery is equal to I1 plus I2. All right, now we know that delta V, again, Ohm's law, super important, delta V equals IR. We know that the I is equal to V over R, right? So we can replace all of our I's with just the delta V over R. All right, so that's what they've done here. Now we know that in a potential difference, or in a potential difference in a parallel circuit, the potential difference are all equal to each other. So that means all these potential differences can cancel with one another. And so this is how we derived this formula here. And so what does that mean to you? This is what it means to you. All right. This is our formula to calculate the resistance of a circuit that's parallel. R over the equivalent resistance equals R over R1, 1 over R1 plus 1 over R2 plus 1 over R3. All right. And again, here's your steps to solving for a parallel circuit. All right. Again, number 1, always find the equivalent resistance. All right. Number 1 step. Number 2, use the Req with Ohm's law to find the delta V or the total current, and then use the potential difference to find each individual currents. And then obviously you're just going to use Ohm's law to do that. Let's practice a parallel circuit here. It says find the equivalent resistance, the total current drawn by the circuit, and the current in each resistor for a 9-volt battery connected to each of these things. All right, so this first one here, we've got a 9-volt battery connected to a 30 ohm resistor. So here's our 9-volt, here's our 30 ohm resistor. All right, and we want to find the total current drawn by the circuit. Well, this one's easy because this is exactly what we've just already done, right? So the current is equal to just delta V over R. All right, so the delta V, well, that's just 9, and the resistor is 30. So we just take 9 divided by 30. Divided by 30. All right, and you get 0.30 amps. All right. And then the current in each resistor, well, we know that in a parallel circuit or a series circuit, it doesn't really matter. The current's 30 overall, there's one resistor, the current's 30. Now we have 3 of them, right? So it's the same idea, but now we've got 3 of them, so I'm going to draw it a little different, like this. 1, right? And so this one's 9, this one's 30, this is 30, and this is 30. Right? And so essentially what we've got is we've got a different little thing. So number 1 step is find the equivalent resistance. So the equivalent resistance for this guy is going to be equal to 1 over 30 plus 1 over 30 plus 1 over 30, and then all to the inverse 1. All right, so we're going to take 30 inverse plus 30 inverse plus 30 inverse, and then inverse the whole thing. And so we get an equivalent resistance of 10 ohms. All right. Now that we've got that guy there, we can, I can't remember where I put my face. All right, I'm up here in this video. All right, so we've got, now that we've got 10 ohms here, all right, we can use this guy to find our total current. So current is equal to delta V over R. So our delta V is 9 and then over 10. So the total current is 0.90 amps. But that is not the total current. That's not the current across each resistor. Remember, because once we're in parallel, the current across each resistor is equal to all of them, each of the currents across each resistor has to add up to be the total current. All right. Now the nice thing here is that because each resistor is equal to each other, that means the current has to be equal across each one. So the current across each of these resistors, all right, is just going to be equal to 0.9 divided by 3, or 0.30 amps. All right. All right, so there you go. Nailed it. So this guy here, this is where the rubber meets the road. All right, these are your 2 big guys you're going to work with: your series, your parallel. This is generally how they're written out. These are the rules for current. These are the rules for potential difference. These are the rules for equivalent resistance. This is a really, really important little table here that kind of wraps up everything we've talked about in the last couple of minutes. So take a moment, take a screenshot, or a, I'll post for it. Take a picture, whatever you want. Okay. So if you're wiring lights, why is this important? Like, just, the basic bare bones, like why do we care about equivalent resistance and all this stuff? So think about it this way: if you have your light bulbs hooked up in series, and then you take the bulb out of one of them, or one of your bulbs goes out, the electricity can no longer flow through here. This is no longer a closed circuit. It is open. So electricity can't flow. So if this bulb disappears, your electrons can't flow. You do not have a current anymore. You cannot have light. All right, so if you've seen the movie Christmas Vacation with Chevy Chase, he spends like a good chunk of the movie just going in the garage trying to figure out which of the bulbs in his Christmas lights has gone out, because his Christmas lights were in series. Now, if you take your bulbs and you wire them parallel instead of in series, then it doesn't matter if one of these goes out. all right, then you'll still have current going through the rest of them. Your electricity will still travel through them just fine. All right, now the question is, which one will be brighter? Well, the parallel one will be brighter, but it'll also draw more current, so therefore it'll also cost you a little bit more money. All right, so that, it's kind of a trade-off a little bit, and it also costs costs more to make because it uses more wire and so on and so forth. All right, so that's it for now. Do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.